Okay, as I promised in the previous video, I'm going to provide the generalization, or what you could say, proof that the method we used in the previous video is valid and can be applied more generally, although we have to recognize that this is only in a special circumstance where on the limits you have a circumstance where you have a function in that the limits of the function are involved in the argument of the function, as shown in the denominator of this integrand. So here we have the limits, or the sum of the limits, subtracted from the variable of the function, x. And this is not a case that you run into very often. I mean, this is really a special case. It does apply to a number of different functions that other than the ones that we presented. And what I'm talking about is the integrand, where we had sine of x over the sine of x plus the cosine of x. And cosine of x is really equal to sine of x 90 degrees minus x. So we have a situation where we could use a u substitution where minus x, where a equals 0 and b equals pi on 2. So that's what we had in the previous problem, and that's how we could use this method. And what we're going to do now is prove that this method is indeed valid, and that we can apply it to other functions. But again, how often do we find the argument of the function where there's a difference between the sum of the limits from the variable? It's a limited it's a limited method, but you can integrate, actually trivialize the integration of functions of this type and solve them. I tried other means. I really worked at it, and I wasn't able to find another method. I tried all kinds of substitutions. I tried using partial fractions, and I wasn't able to solve this particular function, or integrand. So this method was about the only method that could give me a result. So maybe that's my own limitation, but I worked at it for quite a while, and the only method that worked was the method here that is presented in this video. So let's get started. Well, the generalization is really not that hard. The proof that this works is really not that involved. I mean, it's kind of interesting. It's neat. It's really basically the approach is to transform the function, the integral, into another form that's equivalent, and then add the two together and end up with an integrand that leaves you with a ratio of 1. So basically, the integrand becomes dx. So let's take a look at how we do this, okay? So we say that I of x, I of x is equal to this integral. And then we use the substitution for the argument of the integral, so we say that u equals a plus b minus x. And then du equals minus dx. So what we need to do is first, this is one of those cases where we do want to figure out the limits. So in this case, when x equals a, u equals b, and x equals b, u equals a. So we have a reversal of the limits. We have an integral that goes from b to a. And we have f of x, a plus b minus u times minus du over f of u plus f of a plus b minus u. Okay, so now we've got a transformation of this function, the integrand. Whoops. Keep forgetting my finger can do that. So here we have a minus sign. And so we've got to deal with that. Well, how we deal with that is if we switch the limits to a to b, we must put, I do this sometimes. We must put a negative sign there when we swap the limits around. So when we go from b to a to b, we got to put a negative sign right there. So we've got that negative sign, and we have f of a plus b minus u times minus du, but we know that the negative signs cancel out. And then we have f of u plus f of a plus b minus u. Okay, so we end up with I of x looking like this: a to b, f of a plus b minus u over f of u plus f of a plus b minus u du. So we got an alternate form here. So this actually, we really should be technically saying I of u. But I could change the variable. I could say I of x just as readily. Oops, I'm not being sloppy here. I could make this a plus b minus x dx over f of x plus f of a plus b minus x. So we have two representations. We have this representation and we have this representation. So now we just add them together. So let's take a look and change the sheet. So we have I of x plus I of x, which is equal to 2I of x, and that can be equal to a to b f of x dx. Whoops, what am I doing? That's the previous problem. F of a plus b minus x plus f of x plus the other representation, which is equivalent, f of a plus b minus x dx over f of x plus f of a plus b minus x. So that's what we have. And because we have the same denominators, we can add the integrands. So we have 2 I of x equals a to b, where we have the integrands added together. The numerator and denominator. You can see that the denominators are the same. And in fact, when you look at the numerator and the denominator, they're the same. So they cancel out. And all you have is 2ix equals a to b dx. And that just gives you x b to a equals b minus a. So I of x equals b minus a on 2. And you could, again, this is only under special circumstances. This is not something that you can use more broadly. It's very specialized. You have to have an integrand where that is true. And that is the case. If you don't have that circumstance, you can't use this method. It's actually a trick or a clever for a very specialized case. But you can apply it to various functions. I mean, the integrand that we looked at in the previous problem was sine of x over square root of sine of x plus the square root of cosine of x. And cosine of x really is sine of x, as I mentioned before, pi on 2 minus x. That's equal to the cosine of x. So we really do have that circumstance. If the limits are a equals 0 and b equals pi on 2, then a plus b equals pi on 2, and then we have our argument. So if we have other limits, for example, if a equals pi on 6 and b equals pi on 2, we'd have to break up the problem in such a way, in fact, it can't be done because we don't have an equivalency where, like, for example, pi on 6 minus x, well, what is that? There's no equivalency that we know of. So that wouldn't work. So again, it only can be used in very special circumstances. But again, you have to be on your toes. This is a method. It's good to have in your hip pocket. Be aware of that it exists. You're not going to find that you have opportunity to use it too terribly much. But be aware that it does exist and that you can apply it under certain circumstances. So with that, the generalization has been established and the proof has been given that the integral in this particular case, and this is the case that was given in the problem before, is indeed valid, where I equals 0 to pi on 2 square root of sine x ex square root of sine x plus cos x equals pi on 2 minus 0 on 2, which is just pi on 4. And there could be any number of let's say f of x is equal to x squared. And we have the circumstance where we have I equals 2 to 4, and we have x squared dx over 6 minus x squared plus x squared. Now, if we have a situation like this, then we have 4 minus 2 on 2, which is 1. And we could go through the logic, but we've already proved the generalization, and so we don't need to do so again. We don't need to pick out we could if we wanted to, but it would just yield the same result, and this would be the net result. It's just something to note when you have a situation like this. I mean, it's very specialized. Okay, so with that, I'm not going to spend much more time on this. This actually, I had hoped that I could find a way of solving this independent of the the method provided here, because I don't necessarily care for clever tricks, and there must be a way. I just haven't thought of it yet. I spent some time trying different techniques, and I wasn't able to solve the integral in any other method. It should be. There should be a method, but I just wasn't able to do it, and I didn't have a whole lot of time to really spend on it. But I did take a little bit of time, and I'm still not satisfied. I think I'll come back at some point and try it again. Maybe this is just one of those special cases where there's no other way of approaching it other than this, and it's just one of those one-offs, as we call it. Okay, so anyway, this Math Man wishing you the best.